Show you a little bit of a deep dive into IBM's GPFS, which is a cluster file system, and we had some layout problems. We couldn't attach to the screens right here. This is why we have a setup like this. I hope that my laptop is not going to fall down. Anyways, this is the agenda. We're going to talk about the technology overview first, so we are going to give you a deep dive into how GPFS works. We are going to stick to this threefold structure, so basically we're first going into a local attack vectors for the file system for GPFS. Then we are going to take a look at the remote view. How does GPFS, the attack surface of GPFS, look from the outside to an attacker? And then we're going to the core, which means the kernel modules and all that is in the core of GPFS. And hopefully we will have a chance to have a Q&A session afterwards. So to give you a technology overview real quick, IBM's general parallel file system is a cluster file system. We named our talk General Broken File System because we think that quite a lot in the architecture of GPFS is flawed, as you will see in a minute. It claims to be fast, simple, and scalable, which is, we took that off of the website. We have no idea if it's really fast, simple, and scalable. And it basically works like multiple nodes that get interconnected to each other, and you have like two main operation modes on it. One is like the SAN mode, which means that the nodes are connected to a SAN, and the other one is network shared disks, means you have a disk on one of the nodes, and you can share this data that is on the disk throughout the whole cluster. There are different operating systems supported. We are looking, or our research was based on GPS 3.5 on Linux, and you can get it for Windows, for Unix systems, and for Linux, basically. They support all operating systems. It has a really long history, so when we found, or when we were researching it, we encountered it at the customer site doing a penetration test. And we were looking into how to gain higher privileges on one of the nodes that we had low privilege access to, and we found binaries that started with TS and MMFS. TS is kind of the tiger shark file system, so there are binaries from like 1993 laying around on the file system that are used to administrate the cluster or the node. And then you have like MMFS, which is the multimedia file system. So this technology is quite old, as you can see, 1993. And it is basically used in many supercomputers. And it's basically, if you have a cluster architecture somewhere and you need to shove around big data, then there's a high chance, a high probability that you can encounter GPFS. We even heard that some of the three-letter agencies are using it to do, I don't know, research, I'll call it. Okay, so what kind of components are in there? We have basically this threefold structure. We have user space utilities. These are basically the ones that you've seen here. They start with TS or MMFS. There are more than 200 of these binaries on the file system. If you install GPFS, there are a bunch of shell scripts laying around, and basically most of them are just symlinked or plain copies of a handful of binaries. So when you start the binary, it basically starts to detect how its own name is, and then it starts to do something. Some of them are set UID, which makes it a prime target for an attacker, for a local attacker. And this basically sums up the user space utilities. So a lot of user space utilities, and they mostly share vast code bases. Then you have the communication daemon running on all of the hosts. It is called MMFSD. And it uses a proprietary communication protocol via TCP to shove around the data, to get information. One of the main parts is the kernel module, or the two kernel modules, basically the two kernel modules that are rolled out. The core kernel module is a binary-only kernel module, and then you'll have a wrapper module around it that is available as open source, which makes it quite nice to research. Okay, so coming from this, user space utilities, communication daemon, and the kernel module, we need you to remember this structure. We've built up a small checklist for you, so remember this structure in your talk. We have user space utilities, the communication daemon, and the kernel module. And as you can imagine, we will start right away with the user space utilities. So as I said, we encountered GPFS in a project at a customer site. We were researching on how to gain higher privileges on the system, and we were looking into, or we were identifying set UID binaries that are on the host. Everything you see right here is like Tiger, Shark, administrative tools, and the ones in red are the set UID binaries. And if you look at one of those, or the first one that we picked was TS status, because it sounded quite simple, and what it does, if you start it, it simply prints you out if the file system is running or if it's not running. So just, that's it. Then you can feed it arguments. We found out that you can basically, I think, only put one argument in there, and this argument is the name of a file system. So what you can do is you can check if a known file system in the cluster is still alive, if it's there, if it's connected, and what's its status. And the first thing that we tried is putting a bunch of A's in it to feed it a bunch of A's. We knew it was like must be an old binary, it's quite old, and we fed it a bunch of A's, nothing happened, there is a check. Nevertheless, it's using a lot of string copy stuff, but everything was safe from this perspective. And the next thing that we did was we fed it a classic format string to see if something is happening right here. And as you can see, the %x right here gives us something that looks like an address. So the output is not what we fed into the binary now. It seems to be something that is coming off the stack. So this is a classic indicator for having a format string vulnerability in the binary. And it's a set UID binary, as I mentioned. Okay, now by specifying multiple %x's, we were able to retrieve stuff off the stack, as you can see here. Looks, again, like a classic format string approach. We then used the %n identifier to see if we're really still in format string, and as you can see, and a segmentation fault happens. This is why %n basically writes the number of bytes written so far to an address in memory, and if this happens, most likely you will crash the binary, and this is what you can see here, what is happening right here. Next up was the %s. We tried to feed it a %s and see what was going on, and as you can see now, basically what we've expected is, that's magic happening right here. Thank you very much, that looks better now. So the %s that you can see here should also retrieve stuff from the stack, but as you can see is we get an error message stating that we have lost connection to the file system daemon. So investigating this issue a little bit further, we saw that we were able to crash the file system daemon with the %s identifier, and we actually had no clue why this is happening. So %x behaves like a normal format string, %n crashes this binary right here, expected behavior, %s crashes the file system daemon, and we were like, what? Why is it crashing? So we thought this is a pretty standard format string vulnerability, and this should be exploitable. And we were looking at how to exploit it. We were looking into the binary a little bit, but there was still this question hanging around, why can we crash the file system daemon with a %s? So what we did, first of all, was because the guys that we were pen testing put a little pressure on it, and we reported this vulnerability instantly to IBM, but we did not submit an exploit. We just used the proof of concept that basically had the memory corruption or the format string in it, and was showing then we were able to crash the file system daemon, and this looks like a classic format string vulnerability. So they put out a CVE. The CVE was kind of scored pretty low, most probably because we did not submit an exploit for it. We just used the denial of service proof of concept. This is why they scored it with a 4. And if you read over the security announcement or the CVE, you see that a security vulnerability has been identified that can result in a denial of service. We kind of thought at this point of time, this is a classic format string, so this should not only be a denial of service, but rated a little bit higher. and they stated has not yet shown to cause any other side effects besides the program terminating, and it affects a set UID command. So by reading this CVE, we thought, challenge accepted, we need to provide something that kind of does a little bit more besides just crashing the file system daemon. So we had our research time. We were debugging a little bit. As I said before, this bug completely looked like a normal format string. We still didn't know why MMFSD was crashing. We just ignored this fact and went on researching on what was happening. And what we found out by using strace is that if you start the binary TS status with one argument, the TS status will bind to a random TCP port on all network interfaces. It will then send the port number and the user-supplied input into a local message queue. Then the file system daemon, after reading the message queue, connects to the port and sends the result back to the binary. I'm going over this quite slow because you have to understand what's really happening here, because this is really critical. And then TS status simply is printing the result. So again, you fire up the TS status binary, it writes its port number into a message queue, the daemon is looking into the message queue, picking out the port, connecting to the binary that you just started, and is giving you input based on the input, that the user-supplied input you fed it. Okay, but wait. While analyzing this behavior, especially the part where the MMFSD is connecting to the port, to TS status, and sending back the result, we were encountering this. Now, if you look closely at this, this is again an strace output. You see like a read here, which is coming over the network. So this is data that is coming over the network. And then you see a write here, which is the error message that is printed out by TS status. What you see right here is that they're actually sending a format string over the network. So we are not getting this error message as a string over the network. We are getting an error message with a format string and the corresponding stack for this format string over the network to the binary. So, going back to the walkthrough, if the file system daemon connects to the local port, it does not send the result, simply the result, but it sends it formatted as a format string plus the corresponding stack. And because this stack creation does not support %s, this is what actually crashed the MMFSD, because they did not implement like the %s identifier, and that's why it just simply crashes. Okay, so this was the reason why MMFSD is crashing. So, but keep in mind, what is happening right here is the MMFSD is sending a format string and the corresponding stack over the network. So, we came up with some ideas for the attack. What happens if we connect to TS status instead of the MMFSD? Send over the format string and our control stack. We can influence the stack and control it completely, so that should be really straightforward for code execution right now. But we have two challenges right there. One is speed, and the other one is the random port TS status is putting up when it is starting. So for the random port, we did some research and we reverse engineered the binary, and we found environment variable GPFS CMD port range, which you can set to arbitrary values, and then TS status will luckily pick this port that you specify. So from a local attacker point of view, this is good, because we don't have to deal with a random port. We can just specify the port. And for the race condition, connecting to the TS status binary to the specified port earlier than the MMFSD, we had just to be faster than MMFSD. The race is easy to win on a multi-core system. We tested it on single-core systems and we're not able to win the race all the time. A colleague of us just said, like, why don't you just put a few more CPUs into your virtual testing machines, and that basically worked. So we were able to, I would have guessed that we would even have been able to win the race with Java. Now we're using Python and that works fine. Looking into it a bit more, we had some problems establishing a connection or to send over the data that we wanted to send to TS status. And looking at the binary, we saw that there is a cookie value, some kind of cookie value. And attaching a debugger and looking at it in a little bit in more detail, it turns out that this is just the PID of TS status. So the whole authentication that MMFSD is giving TS status is basically its PID, the process identifier. So the exploit kind of should look like the following. First part, we are setting our port with an environment variable. We then win the race against MMFSD. We are sending TS status its PID for authentication. And in the second part, we just do our job, do code execution, and that's it. Pretty simple. So we have an arbitrary write by using the %n modifier. This is how we tried to achieve code execution now. And so we have this format string and our control stack. We have an arbitrary write. The binary is not pi enabled, so we have constant addresses, which is quite good. Although the system libraries and stack heap addresses are randomized, we are encountering the problem that we cannot do an information leak. So normally when you have a format string vulnerability, you can leak stuff from the stack and see if there are some interesting pointers, and if these pointers are there, then you can calculate your offsets and just try to get your exploit working. In this case, this is not something that we can do, because in our case, we control the stack. So the stuff that we are giving as the stack is not a real stack in TS status, it is the stuff that we are sending over the network. So an info leak is not possible. Then we decided, okay, what can we override? Still override. We went for function pointers, namely the global offset table, and we just tried to override library functions. So what we needed to do is find a library function that is called after the format string is triggered, override its pointer, and let it point to the start of our rob chain, for example. The problem is that the binary is quite small, and we could not find a usable stack pivot to start our rob chain. So, okay, so we were sitting there having like problems getting our rob chain to work. We came up with another idea. We will just override the library function or one library function with a different one. For example, we will just override the pointer to printf with the pointer to system. The problem here is that we could not find any compatible library function. So this, from the perspective right now, looks quite hard, because you can't just start off your rob chain, you cannot override function pointers to point to interesting functions like system, and we were basically nearly at the end. But then we came up with an alternative approach. By reversing the binary a little bit more, we found out that the communication between MMFSD and TS status is basically using different kind of message types. So the first message type that we were using was display message. It just does what it says, it displays the message. Then you have general error. We didn't even take a look at this one. I have no idea what it does actually. It works a little bit the same like display message, but we didn't look at this. And then we stumbled upon edit message, which is quite interesting, because edit message basically does what it says. The server sends edit message with an arbitrary text content. The command line tool writes this content, or TS status, we're calling it TS status in our case, writes it into a temporary file, drops the privileges, opens the editor specified in the editor environment variable, and lets the user edit this text. You can see that right here. So we have like the environment variable. If this is not set, it drops to VI. Then it's doing dropping privileges and executing the editor with the text that we are sending over the network. So the user can edit the file or the message, save it, exit the editor, close the editor, and the data is sent back. So what we're going to do with this now is we are sending 3 messages. The first 2 messages will override the set group and set user ID with the address of a ret instruction, which basically means that we are going to knock out get set group ID, set UID. So this should not drop privileges right now. The third message will then trigger an edit message command, which basically sets the environment variable to user bin Perl, and the text that we are going to send over is simply something like this. We're using set UID, set group ID, and then we're dropping to system bin bash. I'm going to give the control flow back to Felix right now because he's going to demonstrate you how this is going to work.
Okay, so it seems to be working. So unfortunately the resolution is a bit bad, but I hope you can see the exploit still. So on the left side we start our exploit, which is basically just a Python script trying to connect to our port and sending the format string as well as the other messages. So this should normally just hang a bit. And on the right side, we start the TS status binary. So this is the one we actually want to exploit. And you can see we have like the editor environment variable called TS status, and we have the port variable setting it to a fixed port. Check. Okay, yeah.
So could you adjust the screen size a little bit so we can see the last 3 or 2 lines just for convenience? If this is possible, thank you.
Okay, hopefully it's working. So now we have the exploit running on the left-hand side, and I'm trying to... And I'm now starting the TS status binary on the right side. You can see we are the low priv user. And now we see on the left-hand side the exploit actually triggered, and on the right-hand side you see a lot of zeros. And these zeros are the format string that's actually printed out, because we use the %n exploit to override an arbitrary function pointer, and like %n works by specifying the number of characters already printed. So we print a lot of characters. This will take a couple of seconds. And at the end, you should see that we are running as root. Yeah, it's still running, so you won't see anything else than zeros for now.
Yeah, we try to put in some ASCII art. Oh, I need to take the microphone. So we were thinking about putting in some ASCII art so that this 1 minute or 45 seconds will not be that boring, that you only see like nulls floating around. We also came up with the idea to do some dancing while this is happening.
Okay, so no dancing for now. As you can see, we now have a shell, and if I enter ID, you can see we are now root. So that's... Thanks. Now I'll switch back over to Florian for the slides.
Okay. Where am I? Okay, so after submitting this again to IBM, we got another CVE, and the base score is a little bit higher this time, as you can see, 6.9, and they kind of described what is happening right here quite good. So coming back from the only denial of service, keep on passing, there's nothing to see, to 6.9, and CVSS base score is quite good. So looking at the user space utilities right here, we kind of solved the problem for the local privilege escalation, and we managed to get like a full-blown local root exploit for this.
So this is already quite nice, but of course this is like a local exploit on a local node in the cluster. So we have like multiple nodes in the cluster. If we have a local user account on one of these nodes, we can compromise it. Now the next step, of course, would be to compromise other nodes in the cluster. So we are thinking about what would be a cool exploit to gain access to other systems. But if you actually start looking into the GPFS documentation, you see this statement. So a prerequisite of the general parallel file system is actually that you are able to SSH from one node to another node using the root user ID without a password. So they have to have the SSH keys pre-configured that you can simply SSH into other nodes. So like if you compromise one node in the cluster, you will get root access to all nodes in the cluster. And there's even built-in functionality for this. So there's this comment that's named MMDSH, which probably stands for Multimedia Distributed Shell or something. And you specify the command you execute and the nodes you want to execute on. And then you get like the return, the output returned. So we can see we can now execute commands as root on all systems in the cluster. Now, this is interesting, but still a little bit boring because we are still requiring to have like one local account, low privileged account on a cluster system or on a cluster node. So what would be much more cooler is if we just could exploit GPFS completely from the remote side. So the main attack surface for this is the MMFSD, the Multimedia File System Daemon. Magic again? Okay, thanks. So this is the main network daemon that runs and used for the communication of all the nodes in the cluster. And it's running on port 1191 on all the interfaces. This is interesting because like if you imagine a supercomputer that has multiple network interfaces and some of them are used for GPFS communications, but some of them are open to the outside, to the internet or to the office network, then the daemon will by default run on all these interfaces. So you can compromise it potentially from an interface that isn't even used for GPFS communication. And the daemon is mainly used for the cluster communication, for synchronization between the states. And if we are using GPFS in the network shared disk mode, so you don't have like a SAN backend in the end, then it's also used for this network sharing of disks. It works by that all cluster nodes open multiple persistent TCP connections to each other, and then they mainly communicate using like heartbeat messages, so all the nodes are still alive, and file synchronization if file access happens. And what's interesting, if you look at the cluster communication, so just open Wireshark and look at GPFS communication, you can see that by default, all file accesses are completely in clear text. So if somebody is writing into a file or some file on a network shared disk is manipulated, you will simply see it in clear text. This is quite nice, but still, it might be a possibility that there's no sensitive data on network shared disks, so we won't see anything interesting. And very often GPFS is communicating over private network interfaces. So gaining a man in the middle communication for GPFS communication is kind of hard. So still, if we have like the possibility to perform a direct attack on MMFSD, that would be really great. So we started to analyze the protocol for a bit. It's a stateful protocol, so it builds up a connection, a persistent, which is created using the hello packet, and after that you exchange the actual data packets. And so the problem is you can't simply replay one of these data packages. Instead, you have to create a valid hello packet to build up the connection. Now, SSL is possible, but due to performance reason, not used by anyone in production. So normally, and the default is completely unencrypted. So if we look at such a hello packet, We have some highlighted stuff. And if some of you guys are fluent in reading hex, then you probably already recognize the green and the blue one, which are basically IP addresses. And they are the IP address of the source and of the destination node that are communicating with each other. And the interesting thing is, this is not in the IP header or something, this is inside the TCP payload. So you have like, you specify the IP address inside the TCP payload again. And then you have like, at the front you have this magic constant, which is simply a constant used by GPFS. You have timestamps, you have a cluster ID, and then it's like TLV, so type, length, value. So pretty standard stuff. Now, what kind of authentication is actually used in this hello packet? Because you don't have like something like a password or anything we did see. So when we analyzed the binary, we saw that the only kind of authentication they're actually using is that only communication between nodes in the cluster is allowed. And this check is performed based on the IP address, but it's not performed based on the IP address that's in the IP header, which would be pretty hard to spoof. Instead, it's performed on the IP address in the payload. So if we simply put a valid node address in the payload, then we can communicate as part of the cluster. Of course, this opens up an extremely large attack surface because it's a distributed file system. So if we can just spoof that we are part of the file system by design, we have like a lot of possibilities like manipulating data, corrupting data, and stuff like this. But for us, we were more interested in getting like direct remote code execution. So we started analyzing the protocol used for the internode communication. And if you spend some time searching for interesting message types, then you find something or a function called handle cc message remote, which is basically some kind of RPC message mechanism. It has the message type hex C. And what it does is that you simply call this method using a GPFS message. And the payload you send, in addition to this message type, is attached as argument to one of 3 command line tools. So command line libraries or binaries that are lying on the local file system. They're called remote, rts, and help. And what's interesting for our system, only remote actually exists on the file system. So this functionality is so old, most of it doesn't even work anymore. And so now if you find a command injection in the remote binary, then you have like completely remote code execution. And if you look at the file, you actually see it's not a binary, it's a bash script. And if one of you ever audited a bash script, normally you find like command injection vulnerability every 5 lines or something. In this case, this is actually really good. So it has like 4,000 lines of code. And by design, so without any command injections or something like this, you can actually unmount file systems, mount file systems, or uninstall the GPFS daemon. But somewhere in the code, you have this command injection. And so basically, if you're on the local system and you would execute this command, you would create a file temp pound in, you would create an empty file temp pound. Now, of course, using this message functionality I just presented, you can actually do this from remote just by connecting to the GPFS daemon without any kind of authentication. And of course, this command executes as root. So this is a remote root exploit without any kind of authentication. So I have to switch again. Oh, Florian, can you switch it for me? For the demo. So the demo setup is a bit more complex because basically like the command injection is limited to a certain number of characters and really limited what kind of special characters you can use. So what we are doing here is on the top right-hand side, we are starting as an HTTP server. And our exploit actually, the first command we execute on the remote system simply downloads a back connect shell from this web server. And the second command and execution we will trigger actually executes this back connect shell to connect to our netcat listening on the left-hand side. And this is the actual exploit. The whole communication is kind of racy because we are spoofing like a node that actually exists in the network. So sometimes we have to execute the exploit multiple times. Yeah, as you can see, I needed to execute it multiple times. Then you can see like the connection to get the back connect shell. And on the left-hand side, I have a shell, a reverse shell. And if I enter ID, you can see again I'm root. So, thanks. So this is a completely remote code execution with root privileges without any kind of authentication. So this is like the point where it's game over.
The second time.
Yeah, the second time. Now, if you still remember the structure of our talk, then we have like, oh no. So we reported this bug, and after like the bad CVSS score for the first bug, in this case they agreed with us this is something critical, so we got a 9.3. So it seems IBM learned their lesson, and now they will give higher CVS scores to our vulnerabilities. But if you remember the structure of the talk, we still have something left. So we have the user space utilities, we have the communication daemon, but there's still this interesting looking kernel module. Now, the kernel module, or like the whole setup, is on Linux basically that GPFS creates a device, SS0, and this is used for the communication between all these user space utilities and the kernel, and it's using normal Linux IOCTL calls. The problem is that there are actually core libraries, so stuff you can use in your own application, which use this interface to communicate. So it's not possible to simply set a device permission for root only, so this device, you can use this device as a local low-privileged user. Which means all the IOCTL calls actually have to implement their own permission checks. And there are like 150 of these, so this is again a really large attack surface. So we started auditing these kernel modules. And basically they have like 3 kernel modules, but MMFS Linux is just some kind of GPL wrapper they're potentially using to don't violate any licenses. So the actually work is performed by MMFS 2.6. And you can simply put it in IDA and start auditing all the IOCTL handlers. And I basically started with IOCTL 1. And if you come to IOCTL call number 39, which is kernel wait for flock, which is probably file lock or something like this, then you see there are no privilege checks. It's called with user-controlled arguments. And if you look at the code, you potentially see the problem. You have an arbitrary write. They take the default argument you specify in the IOCTL call, dereference it, and write a value you put as the first argument. So this is like, if you ever exploited the kernel bug on Linux, this is like the most trivial to exploit bug class in general. So we reported this, but again, we made the mistake to not supply a full code execution POC for this. So they didn't learn the lesson, because basically they patched the bug, but decided arbitrary write in the kernel that looks harmless, it's probably only a denial of service bug. No code execution possible. Of course, that's false. So you can use this arbitrary write to write the address of our own ring0 shellcode into an unused entry of this GPFS IOCTL handler table. Then we call this back.ioctl. The kernel executes our shellcode and changes the privilege of the current process to root. Again, we have a demo. This time, the demo even has a really cool logo. And designing this logo actually took longer than writing the exploit. So it wasn't that hard. Okay, switching back to the different microphone. We are back at our low privileged user account. Switching to the right directory and compiling our kernel exploit. And if I then start it, of course the logo doesn't work with this resolution. That's unfortunate. Yeah, but it works like this. So this took some time, and it took longer than the exploit. If I now enter ID again, I'm root using a kernel module exploit. Thanks. And now we have like 2 minutes left, so just for the recap. Yeah, if you remember the structure of a talk, we had the user space utilities where we had a local privilege escalation. We had the communication daemon where we had a remote root vulnerability, an unauthenticated one, this one. And we had the kernel module where we also got local privilege escalation via an arbitrary write. And so we have to say something to IBM's response. It was a really professional handling of this whole stuff. They still have like this optimistic estimation of exploitability, but they released really working patches for all these 3 bugs. They even released them on a Sunday, so they really spent some time doing this. And they needed like 30 days from our report to the day they released the patches, which is in our impression really impressive. The problem with the vendor patches, so you should definitely apply them if you use GPFS, that the actual remote exploit, so the problem that you don't have like an authentication for this communication and you can spoof the IP addresses, isn't actually fixed because this is a design problem. And the remediation is that you have to enable SSL. So if you use GPFS in an environment where an attacker could probably reach an IP, you should definitely enable SSL. Additional hardening is required. Don't have any nodes in your cluster that you don't fully trust. Again, enable SSL. And if GPFS is only used on one network interface, you should firewall the port on all other interfaces so the daemon can't be attacked directly. Some final lessons learned. Basically, attack surface is the key. If you have a large attack surface, you will get problems. Complexity kills, because GPFS is like a really impressive architecture and implementation, but it's incredibly complex, incredibly old, so you will find bugs in it. And never give up, so even if some of these bugs looks a bit tricky, in the end you probably get a working exploit out of them. So thanks for your attention, sorry again for the problems with the technical stuff, and we are happy to answer some questions, I guess. Thanks. Any questions? Doesn't look like it, so thanks again.
Thanks, bye.